Let's continue with our chapter number 3, which was of force and motion. This is the part 3 and the final part of this chapter 3, motion and force. So let's start with the topic of normal contact force. So the two bodies are said to be in contact when there is at least one force which is either perpendicular or is it parallel to the surface of your contact or the point of contact, which is basically related to the motion of those two bodies, right? So to elaborate this, let's use a help of a diagram. So here we have a couple of figures, right? Diagrams. So let's discuss for every figure what is happening in these diagrams that are illustrated over here. So if you look at this diagram, you immediately see that the normal contact force is single, right? So there is only one normal contact force, and that's because only the surface is in contact with this block, right? Now if you look at this figure, you immediately see that there are two blocks, right? We have block A and we have block B, and hence there are two normal contact forces, one on A and the other one is on A as well, right? And similarly for B. And the reason for this is because we have two surfaces that are in contact with each other. Now if you look at this diagram, everything is the same except for the fact that we have three surfaces. So we have this one, we have this one, and then we have this one, right? And hence there will be three normal contact forces, right? And you can see all of them over here. And these are there because of course we have three surfaces which are in contact with each other. Okay, so now if you look at this figure, it looks like there is a rod which is placed on a type of a staircase or something, right? So we have these 2 points over here which are in contact with the rod. So we have this one and we have this one, and hence we have two normal contact forces. So one is this one and the other one is this one, right? So let's just give it n prime, and hence there are two contact points, right? Moving on to this diagram, you have a ring which is placed into this block, and we can see that there are three contact points, right? Hence we have three normal contact forces, right, coming from each point. And here we have a block of mass m, and it is just suspended like that in the air, and hence there is no contact point or there is no contact surface for this block, right? And which means that there will be no normal contact force acting on this block. Now let's discuss a case where we have masses which are connected via some string. So consider this diagram, right? And what is happening here is that we have two masses m1 and m2, and they're connected by this string, and then you pull on mass m1 with force F. This is going to produce a tension in this string, right? So this tension in string is produced for m1, it is over here, and for m2 it is in this direction. And the overall effect is going to cause an acceleration to the left direction where we have the force applied in that direction. So if I apply Newton's laws on this system, so let's first apply them to the mass m1. So once if you say that I'm applying Newton's laws to mass m1, in that case we ignore everything that is, for example, in this case that is m2, right? So you'll completely ignore that thing. And so you see that you have F in this direction, and let's suppose that left direction is positive and the right direction is negative, in that case, defining your coordinate system like that. So let me just do it over here, right? So this is a positive and we have this one as negative. So we define this and then we work with the problem. So you have for mass M1, you have plus F minus this tension T is equal to mass 1 times the acceleration. And the reason there is M1A over here and not 0 is because the force is producing an overall effect of acceleration on this mass M1, which will cause this mass M1 to slide to the left. And similarly for mass M2, you isolate your system only for mass M2, and there is only one force that is acting on mass M2, and that is the tension in the string that is near to mass M2, or that is connected with mass M2, and hence moving this mass M1 by applying force on it is going to cause an acceleration in mass M2 as well. So you have plus T is equal to M2A, right? And here we have then two equations for this system. Now, solving these equations, you come to the conclusion of an expression for the tension in your string, which was developed by applying force F, and that is this expression over here. And you also achieve an expression for acceleration with which this whole system is going to slide to the left, and that is this one over here. So at this point, I would like for you to look at this example, right, and then solve this thing for a case where you have three masses, right? So you have M1, M2, and then you have another one, M3, which is connected by another string attached to M2 and M3. So think of that problem and try to work on it yourself. And then you can share your answers in the comment section below. Now let's start the next topic of projectile motion. So a projectile motion is the one that involves trajectories that look something familiar to this graph that I have drawn. And before we discuss the problem at hand, let's first talk about some of the necessary assumptions that we have to solve the problem of projectile motion. So first of all, the Earth is assumed to be flat over the entire course of your trajectory of the projectile, right? Secondly, the acceleration that is caused by the gravity is assumed to be entirely constant over the course of the trajectory of the projectile motion. Then we have that the instantaneous velocity of your projectile is maximum at the start or at the point of the projection, and it is also maximum at the landing point where the projectile would land and end its motion. Then we have that the instantaneous velocity of the projectile, it is minimum at the maximum height when the projectile reaches this height over here. The instantaneous velocity is minimum, and that is simply because at this height, this maximum height, the projectile is changing its direction to exactly the opposite where it was moving, as you can see, right? And so the velocity component, y component of your velocity, is 0 at this point. So here is a sketch of what a projectile motion's trajectory would look like. So in this figure, the range of the projectile motion is this distance that you see. This is the horizontal distance from the starting point to the end point of your projectile motion, and it is represented with the symbol capital R. And the maximum height that your ball or anything that you have is in projectile motion reaches is denoted with this h and it is the maximum height from this point to this point. So for projectile motion, we have the horizontal or the x component of your acceleration is 0, right? And the reason for that is you have this object in projectile motion, so it's moving against gravity, and there is no other force acting on this object, and so the horizontal force would be 0, which would imply that the horizontal acceleration should be 0. But we have the force of gravity which is acting in this direction, and so the acceleration due to gravity would be minus g, right? Minus 9.8 meters per second squared. So now coming back to this diagram, if you look at the starting point, the point or the angle from which the object is released is noted as some theta naught, right? And with velocity, suppose it's released with some velocity which is v naught, then the horizontal component of velocity will be v naught x, while the vertical component would be v naught y. Right? So if you look at this, after some time has passed, the object has reached this point, right? And you see that the horizontal component of the velocity remained invariant, so it's still the same, right? So you can see that it is still v naught x. While if you look at the vertical component, it is now just some vy. And so vy is not equal to this v naught y, right? So it has some other value now. Similarly, the angle theta has changed from this theta naught to this angle theta, right? And again, you see later in time, the angle keeps decreasing, right? The angle with the horizontal axis keeps decreasing, and the horizontal component of the velocity is still invariant, while the vertical component is changing every time. But at this point of maximum height, what happens is that the horizontal component of the velocity is still the same, it's invariant. However, the vertical component of velocity has decreased to 0, right? So this was retardation, right, as we learned in our earlier video. So what this tells you is, this also tells you that at this point the velocity was some maximum value, when as soon as it was released, the velocity kept decreasing up until where it became 0. And that is what you would expect, right? Because you are throwing it upwards and force of gravity is pulling it downwards, which would cause deceleration, and hence it actually caused retardation where the velocity dropped to 0. And then when the velocity reaches 0, the acceleration of gravity, remember it's downwards, now this ball has to come back to the ground. So the acceleration or the force of gravity would work in favor of bringing this ball back to the ground, and so the path or the trajectory would look something like this, where you see that the horizontal component of velocity at this point is still the same, it's invariant as it was at the starting point of your motion. But the vertical component of the velocity is now pointing downwards, right? And you can see that the theta angle is increasing as well. So you can see at this point there is some vertical velocity again, the angle has increased, and the horizontal component of velocity is still the same. And similarly, you can see at this point we have exactly the same situation, right? So now suppose that I have to write down the horizontal and the vertical components of the coordinates of our projectile motion at some time t. So I would have, we know that the displacement, or let's say the coordinate x, is given as velocity times time, right, in general. But the horizontal component would mean that we should have Vx times time. So the horizontal coordinate is given by this expression over here, where the horizontal component of your velocity v, which is this one, it is actually v naught, so we should have a naught over here, and it is v naught cosine of theta, right? So you can see that this is v naught cosine of theta using trigonometry times time. So that's the horizontal coordinate. Well, what about this vertical coordinate? Will it be exactly in the same way like this? I'll give you some time to think, right? Think and first figure it out, and then I'll write it down so you can check that if your answer was correct. Right, so we would have the vertical component of the velocity. Of course we would. So that would be v naught sine of theta, right? And of course we would have times t. So this thing is definitely going to come. But remember, there is force of gravity acting in the vertical direction as well. It is acting downwards. So we say, according to our convention that we chose for the acceleration due to gravity, which is acting downwards, it's negative g. So I should have another term over here that would account for this force of gravity in the vertical direction, which is this term minus 1 by 2 g t squared. And if you're wondering about this minus sign, it came exactly from this point, ay component, right? So we have minus g. So this is the extra term that we needed to add, and you can even check using dimensional analysis that this has the dimensions of length, right? So which would be the dimensions for this y. Now let's write down some of the useful expressions that we have to calculate some of the quantities for our projectile motion, right? So we'll start with time to reach the maximum height. So what time does it take for this object to reach this height, which is h, right? So we know that the acceleration is given by the ratio of the velocity to time, right? But in our case, remember, to reach maximum height, at that height there is only or at any case, right, there is only one force that is acting on this object, which is the force of gravity. So the only acceleration that is coming from is the y component, which is this one, right? So I can write this expression for the y component as ay is equal to vy over t. And this t is the time that it takes to reach this maximum height h, right? So what do we know about vy? We know that vy is v naught sine of theta. And so this is the expression for ay now, which is ay is equal to v naught sine theta by t. And now what is ay? It is minus g, right? So this is what we would have. Now I know you're wondering that I just said that it is the component ay is minus g, but I wrote positive sign with this g, right? So what could be the reason? Well, take some time, think about it, and then I'll answer your question. Right, so well, that is because as soon as it reaches its maximum height, and then it's going to move forward, right? So it's going to move in this direction. The velocity component vy is going to shift downwards. So there was a negative sign with this v naught as well, like this, and so this negative sign goes with this negative sign, right? And hence the time it takes for the object to reach its maximum height is given by this expression over here. Note that it depends on the angle theta from the horizontal axis, and it depends on the initial velocity that you gave to your object. Next, we have range of our projectile motion, which is this horizontal distance between the point of projection and the point at which it comes back to its level of projection, right? And it is given by this expression over here. By the way, note that every time that I use theta, right, it was actually theta naught, which was the initial angle with which the object was released from the ground. So if you look at this formula for the range, right, what can you tell about when would this range of the projectile motion be maximum? When would that happen? If you think in terms of sine of 2 theta naught, you can immediately see that it would be maximum when your initial value of theta, which was the angle with which you release the projectile, is placed at 45 degrees. So if you release your object at an angle 45 degrees from the ground, that is when you would cover maximum range, right? And that is simply because sine of 2 theta would be sine 2 times 45, which is sine of 90, and sine 90 is maximum value at 90 degrees. We have the maximum value of sine, which is 1, right? And this is another expression for range, and it just relates your range of projectile motion to the maximum height of the projectile, right? And you can see that your range would be equal to h at what angle? It would be equal when theta is at 76 degrees, right? And the reason for that is tangent of 76 would give you 4, and so the 4 would go away with this 4, and you would have r is equal to h, right? And so with all of this, we conclude the chapter number 3 for NET Physics.